Hey everybody, this video is going to be about variation of parameters. In the situation where we would use variation of parameters is this. We need to find a particular solution to a differential equation. It's a non-homogeneous differential equation. But our right-hand side of our differential equation is not polynomial, exponential, or sine or cosine, so our undetermined coefficients technique won't actually work. So the right-hand side on this differential equation might be maybe a secant or a tangent or some other function. So as always, what we do is we solve the homogeneous differential equation, and we get c1y1 plus c2y2, where y1 and y2 are both linearly independent solutions, so obviously these are both functions of t. Now that is actually nothing new. We always do that. Here's the new part. With variation of parameter, we're actually going to guess a particular solution of this form, and this looks really ugly. The y1 and the y2 are exactly the y1 and the y2 that we found, that we know, from the homogeneous differential equation. u1 and u2 are new functions that we're actually trying to find. And I should say I put the of t's next to every one of these functions to emphasize the fact that they are functions of t, but really when I'm working this problem out, I'm going to leave the functions of t off, so our guess is just going to look like that. So in variation of parameters, we always know what y1 and y2 are because we can get them really easily from the homogeneous DE. And the goal is to figure out what u1 and u2 are so that we can multiply all this stuff together and figure out our particular solution to our differential equation. That's variation of parameters. Before we start plugging things in and getting going on this process, I do want to make one note. The note is that we actually need two conditions to find u1 and u2. Just like when we had c1 and c2 in a general solution to a differential equation, we needed two initial conditions to find c1 and c2. We actually need to satisfy two different conditions to find u1 and u2. The first condition is a pretty obvious one. It's the condition that our guess, yp, must solve the differential equation. Now since that's the only condition that actually matters, that this particular solution solve the differential equation, we can make up a second condition wherever we want in this process to make our lives a little easier. So this is to be announced. Okay, let's go through the process. We have a guess. It's u1, y1 plus u2, y2, and we're going to plug this guess into our differential equation right here. To do that, we need to take derivatives, and keep in mind that u and y are both functions of t, so we need a product rule every single time. Now this is already getting pretty ugly, and if you imagine trying to take a second derivative, you're going to have to do a product rule on each one of these four terms, and you're going to end up with 8 different terms here. So remember when I said that we could make up a condition to make our lives a little easier? Well, what we want to do is we want to make up a condition that says that plus that has to be 0. That way we'll only have two terms in the first derivative of our guess, and it'll actually simplify our lives in the future. So I'm going to get rid of this to be announced and announce it right now. Our second condition, we're going to make it up. It's this right here. So I'm going to impose that condition right here, and we're only left with two terms in our first derivative, but we do need to still take a second derivative. Now let's take our guess and our two derivatives and plug that into our original differential equation, just a general DE right here. Alright, I plugged everything in here and it is pretty ugly looking. I would like to group some terms together at this point. I would like to group the u1 terms together, and I would like to group the u2 terms together. So when I group the u1 and u2 terms together, I'm going to factor out the u1 and the u2. So I want to get something that looks kind of like this right here. Here's what happens. Here's what I get when I group all of these terms together. And what's neat is we can make an argument about this big group here, the blue group, and this big group here, the green group. Let's look at this one right here. This is the left-hand side of the differential equation if you plug y1 into it. Now go back up, look at the differential equation that we had. Here it is right here. If we had plugged in y1 into this left-hand side, we would get exactly this blue underlined term right here. Well, what is y1? y1 is a homogeneous solution to this differential equation. So what do you expect to get out of this? Well, since it's homogeneous, y1, you expect that term to be 0. y2, again, we define that up here. y1 and y2 are solutions to the homogeneous differential equation. Again, if we had plugged in y2 into our left-hand side of our differential equation, we would expect to get 0 because y2 is a homogeneous solution. So what we're left with is this equation right here. Now, let me also go back to this other condition that we imposed. We imposed this condition right here. Let me write that down. Now we have a couple of equations, and let's start to think about what we know and what we don't know. Well, we know what y1 is, and we know what y2 is, so we obviously know what y1 prime is and y2 prime. We actually get all of that information from our homogeneous DE. F of t is given to us in the differential equation, and a is a constant in front of our first term in our differential equation. So the only thing we don't know in both of these equations is u1 prime and u2 prime. So what we're left with is two equations and two unknowns. We can solve this for u1 prime and u2 prime. Now you all know my favorite way of solving two equations and two unknowns. It's with elimination. So let's try that here. If we were going to eliminate, say, u1 prime, what we would want to do is we would want to multiply the first equation by y1 and multiply the second equation by a times y1 prime. Then what we would do is we would subtract these two equations from each other. Let's see how that works. Alright, I said I was going to multiply this stuff out, and I did here. Now I'm going to subtract these two equations, and I get something that looks like this because these first two terms cancel out to 0. Now it looks like I have some like terms here. I can factor out an a u2 prime. Now ultimately the goal was to find u2 and u1, so now we can get u2 prime at least by itself by dividing. Oh my goodness, now we have an equation for u2 prime. Now I want to reiterate that everything on this right hand side of the equation we know. We know y1 and y2 from the homogeneous part of our differential equation. F of t is just the right hand side of our differential equation, and a is just some constant that was given to us initially. This all makes up u2 prime. Of course, our goal was to figure out what u2 is, so to get that we just integrate with respect to t. So the other part of the goal was to find u1, not just u2. So what you have to do is you'd have to take the solution that you got for u2 prime here and plug it back into this equation right here. Now once you do that, you can isolate u1 prime. It's actually not as bad as it looks. And you get something that looks just like this. And you can figure out what u1 is, again, just by integrating. Now through all of this mess that we just ran through, all of this derivation, ultimately what we've come up with is two formulas that we can use for u1 and u2 to find our particular solution given a non-homogeneous differential equation that looks something like that. Those two equations that we're always going to use from now on are all the way down here. So variation of parameters becomes basically plug and chug, or plug and crank, or whatever it is that you kids say these days. You solve the homogeneous part of your DE for y1 and y2. You plug all the stuff in here, and you figure out what u1 and u2 is just by integrating. Once you have u1 and u2, you just plug u1 and u2 into your particular solution guess right here, and you're done. You have a particular solution. Now just a note on notation, you'll notice that this denominator here looks kind of like a determinant or a Wronskian of y1 and y2. You'll notice if you take that Wronskian, you get y1 times y2 prime minus y1 prime times y2, which is just this piece right here. So in your book, they're going to use a slightly different notation than I did here. Okay, this video has gone on long enough. I just want you to do one problem for a video quiz. Find a particular solution to the DE using variation of parameters. Again, all you're going to do is use these boxed equations up here and plug them in where appropriate. And good luck. I'll see you in class.